In this video, I will develop the simultaneous eigenfunctions or eigenstates of orbital angular momentum operators L square and Lc. These eigenfunctions are also called spherical harmonics, and we will see why. This lecture is the conclusion of the last several lectures that we have been building up for this one, where we studied orbital angular momentum operators as generators of rotations in 3D space, and also found the eigenvalues of L square Lz operator and their relationship with each other, and also we introduced auxiliary raising and lowering operator L plus and L minus. We will use all of that knowledge now to build the simultaneous eigenstate of L square operator and Lz operator. Now these states, as we will see, and actually we have already seen that they, if we use the label Lm, they depend on these two labels because the eigenvalue of this operator is L into L plus 1, and the eigenvalue of this operator is M. So it is an H bar square here, H bar Lm. Today we want to find this state in position space. More specifically, we are looking for this state in the spherical coordinate system, and since we will see that this state only depends on theta and phi, we don't really need to repeat this R dependence all the time, because ultimately it's only dependent on theta and phi, because it's a state which is an eigenfunction of rotation operators, so R is not involved. And we will also we can introduce notation. This Lm state in theta y coordinates can be represented by this y function with these two indices L and M, and since this is function of theta phi, we are writing it like this. So our goal today is to find these functions which we call spherical harmonics, such that these equations are satisfied. Now, before I go on to find these eigenfunctions of these operators, let me briefly discuss the normalization of normalization requirement of this wave function. Briefly discuss the normalization required for this eigenfunction. The normalization that we require for this can be stated as YLM theta phi mod square integrated over solid angle in all directions should be equal to 1. Which means that if let's say I take this coordinate system here, if this represents the wave function of a particle, then this is probability density as a function of theta phi. So what we are saying here, that probability of finding the particle in all direction must be equal to 1. This d omega is solid angle. Solid angle is defined as the area that let's say any surface subtends when you project it to the origin, and the area that it intersects of a unit sphere. You can imagine a unit sphere here, and this is an arbitrary surface, and we want to find what is this solid angle that is subtended by it. So you project it to the origin, and any area that it covers of the unit sphere is the solid angle subtended by this surface over here. It's exactly similar to the definition of angle in radians, because angle in radian, if I take a little digression here, angle in radian is defined by, let's say you have some curve here and you want to see how much is the angle subtended by this curve. So you project it here and then you draw a unit circle here. So this arc length, which is occupied by this projection of this unit circle, the length of this arc length is the angle, this angle in radian. Because if you recall this famous equation as is equal to theta, if this r is 1, the arc length is equal to the angle theta. Okay, so similarly, the solid angle is the area subtended by any surface when that surface is projected onto the surface of a unit sphere. Okay, this differential solid angle d omega, I can find its expression by noting this thing. That let's say we have a point here and we want to see if we change its angle theta by a small amount d theta, and it's projected here and its angle over here is phi, and if we change this angle by a small amount d phi, what's this area? So this point is projected here, this point is projected here. So if this is our angle d theta, this length and this length is d theta. Remember, this is a small area of the unit sphere, so r is 1. And if this r is 1, this length is sine theta. So this is sine theta. This is sine theta and this is d phi. This is nothing but sine theta d phi. So this length, or equivalently this length, is sine theta d phi. So this area over here, which by definition is this solid angle, is, we can approximate it. If these are differential angles, we can approximate like almost like a rectangle. So this d omega is sine theta d theta d phi, which means that our normalization integral becomes that integral over theta is from 0 to pi, integral over phi is from 0 to 2 pi, ylm theta phi square sine theta d phi plus theta. So our eigenstates must satisfy this normalization condition for the probabilities to make sense. Okay, so having worked out the normalization condition, we are now ready to find these states in the spherical coordinate system. All right, okay. So let me notice this thing, that this L square, when I project it onto this theta phi state, is L into L plus 1 and theta phi Lm, and similarly Lz when projected to position space in spherical coordinate system. So it is an h bar square m h bar theta phi Lm. Now, from this equation, I can quickly find out its phi dependence, which actually we have already done, but let me just review it briefly. This Lz in spherical coordinate is nothing but minus iota h bar, partial to partial phi, and this Lm on theta phi is, we have, let me write it, then I write it. So this Lm m h bar theta phi lm, and this h bar cancels. Let's take this minus iota on the other side, and for this I can write y lm theta phi partial to partial phi. This is iota m y lm theta phi. We can quickly solve this first order differential equation very easily to get y and m some constant exponential iota m phi. And we have already discussed that for this function to be single value, this m has to be integer. And we already know that from these equations and their relationship that m goes from minus L to L, and which means that this m is integer, and also that m goes from minus L in integer steps all the way to L, and since this has to be integer for orbital angular momentum, all of these are integers. Okay, so now we know the phi dependence of this function, that its phi dependence is of exponential iota m phi time. This will help us later on to simplify our equation of L square. I now have to solve this equation, and there are two options. One is that I simply substitute the spherical representation of L square operator here and just try to solve this differential equation, which actually can be done, and it gives rise to associated Legendre polynomials that we can find using series solution method. But since you probably have not studied this method, and we need to have some simpler method to solve it, and also we used a similar simple method when we were studying harmonic oscillator, where we started from the ground state because that was easier to solve, and then using the raising operators we were able to find the eigenfunctions of any nth state. So we'll use the same approach here, that instead of solving this equation directly, I will just try to find this state with maximum value of m, because m goes from minus L to L. This is the maximum value of m, because when m is maximum, when I apply it, when I operate it with the raising operator, I must get 0, because by definition this is the maximum value of m, and the raising operator cannot trace the state after this. Now this is going to be our starting point, and using this we are going to solve for this state, and once we have this state, I will easily be able to obtain other state by operating the lowering operator on this state. If I lower it once, I will have a state just before this one, which is the L minus 1 state, and if I operate lowering operator on this state, I will get the first state before this, and so on. So our focus is going to be on finding this maximum M state, which is an L state. Okay, so to get this state, let me write this in spherical coordinate system, because in spherical coordinate system, this will give us this. We already know the form of this operator L plus in spherical coordinate system, which is h bar exponential iota phi partial to partial theta plus cot theta partial by partial phi over y and L is equal to 0. Okay, so this I can simply remove, because it doesn't have, no, before I remove it, I can notice this thing, that since this YLL is going to have a phi dependence like this, because if this is phi YLM, then YLL will have a phi dependence of iota L phi. So if this is iota L phi dependence inside it, this partial phi derivative will simply give me iota out. I think I made a mistake here. This had an iota here. Okay. So when I operate this with partial phi, we will get iota L. So if I put, let me replace this with iota L, and then there's no phi dependence, I can simply remove this, and we get d YLL by d theta. Actually, better to keep it partial. And when we get iota L here, iota square minus L cotangent theta YLL equal to 0. So this is the differential equation that we can easily solve, because if I take this on the other side and I bring YLL here and take this d theta over this side, I get d YLL. YLL is equal to L. This cotangent theta is nothing but cos theta over sin theta, and this d theta goes here, become d theta. Now you notice this is YLL and its derivative is here. This is sin theta and its derivative cos theta d theta is over here. So I can integrate on both sides very easily to get log of YLL is equal to L log of sin theta plus some constant. Let me call it some C2. Now, if I take exponential on both sides, so this L, we can easily make it power of this sin theta, and this L goes there. And then I take exponential on both sides, so this YLL becomes some constant C3, which is exponential C2 into sin power L theta. So this is our theta dependence in YLL. We have already found the phi dependence here. So now I can write YLL state simply by multiplying this and this, because this is phi dependence, this is theta dependence. So general expression could be YLL, some constant, let me call it C4, exponential iota L phi sin M theta. Now all we have to find is this constant C4, which we can find by normalizing this state. And our normalization integral is that integral over theta is from 0 to pi, d theta integral over phi is 0 to 2 pi, and then I have to take its mod square, it's C4 mod square, its mod square is 1, so its mod square is sin 2L theta, and then we have sin theta, this must be equal to 1. Now this is independent of phi, so this integral evaluate quickly, this is 2 pi, and this C4 is a constant, gets out of integral, so we have 2 pi C4 mod square. Integral is now from 0 to pi sin 2L plus 1 theta d theta equal to 1. Now all we have to do is find this integral, and I can easily find it if I note this thing. That let me label this integral as some integral with index 2L plus 1, because this is the power over here. This is 0 to pi sin 2L plus 1 theta d theta. Now if I break it into two parts, 0 to 2 pi, and let's say sin theta separate and sin 2L theta d theta, and then I use integration by part. So I keep first as it is, and this integral of sin theta is cos theta, applying limit 0 to pi, and then I derivate this one inside the integral. So what I get is actually this 2L 0 to pi sine 2L minus 1 theta plus sine 2L plus 1 theta d theta. Because when I will integrate this one, I will get cos theta, and there is a cos theta coming out of derivative of this, that cos square. I can replace it with 1 minus sine square, and once I put there, I get it split into these two terms. Now, this integral I2L plus 1, you see this is 2L into an integral which has the same form, but index is 2L and minus 1. So let me write it 2L minus 1. This is actually minus sine. So when this is nothing but the same integral as we started, so this is minus 2Li 2L plus 1. So let's bring this one over here. This becomes 1 plus 2L into this. Take 1 plus 2L to the other side, so we get 2L plus 1 as 2L plus 1 I 2L minus 1. So I have been able to write integral with bigger index in terms of an integral of smaller index. So which means that if I keep going, I can write this integral as this, but then I can write this I2L minus 1 as I2L minus 1, and because here it's 1 smaller than this, 2L minus 2, and then I will have I2L minus 3. So I can write that as 2L minus 4, 2L minus 3, and finally I will have integral of 1. And these terms I will get L times, as you can check yourself. Okay, so now I can note a couple of things. If I take 2 from here, 2 common from here, 2 common from here, I get 2 power L, and then I will get L factorial. But over here, I noticed that if I had 2L here, 2L minus 2 here, 2L minus 4 here, and so on, I could get a factorial of 2L plus 1. But since it wasn't there, I can put it myself, but I'll have to then put it over here. So I need 2L here, I need 2L minus 2 here, and so on, which is nothing but the same, these terms, so they will become square. And this I1 is 0 to 2 pi sine theta d theta, and you can integrate it, it becomes 2. So I am now able to get this integral. So we now have this integral, and our C4 is essentially C4 magnitude is 2 into 2 pi is 4 pi, that becomes 1 over 4 pi 2L plus 1 factorial. This is 2 power L factorial, and I have to take square root. Okay. So with square root this goes away and I have to take square root of this term and 4 pi because this is C4 square. So this is our C4 coefficient here. And now we have a complete description of our one spherical harmonic y and L for maximum value of m equal to L. And now I will show how we can use this YLL to find arbitrary, to find spherical harmonics with arbitrary value of m. For that I have to change the board, so let's go to the other side. Okay, so we have been able to find the LL state, which is for the maximum value of m is equal to L as C4 expansion iota L phi sine power L theta, and we just found that C4 is such that its magnitude is 1 over 2 power L factorial 2L plus 1 factorial 4 pi. Therefore, our spherical harmonic for one value of m is 1 over 2 power L factorial 2L plus 1 factorial 4 pi into iota L phi sine L theta. So with this magnitude of C4, our harmonic is normalized. However, in quantum mechanics, there is a convention of having an additional phase minus or plus for either even or odd value of L to have same value of positive value of YLL at theta is equal to 0. Okay, so with this spherical harmonic, we now have our first harmonic, and we can construct other harmonic by recalling that if we apply the lowering operator to any state Lm, what we get is a state with a smaller value of m. So now we have this m is equal to L. If we want to get a state with m is equal to L minus 1, we apply it once and so on. If we want to get a state with m is equal to L minus 2, we apply it twice, and we can get all spherical harmonic for a given range of m, for a given L for all value of m. However, to write it precisely, we need to find this coefficient C minus. So let's take a little digression and find this coefficient C minus. And to do that, let me note that the brass state corresponding to the sketch state is Lm, L negative dagger, C conjugate, L m minus 1. I just wrote the state from the conjugate of this thing, but L minus dagger is nothing but L plus so if I take an inner product of this and this state, the left side on the left, right on right, we get Lm, L plus, L minus, Lm. This C minus conjugate, C minus, so C minus square. This Lm minus 1, Lm minus 1, see these are of the normal state. This is 1, so it's gone. And if I substitute the expression for L plus and L minus in terms of Lx, Ly, we have done it several times, so I'm just going to write it. It comes out to be L square, Lz square plus H cut LC which means that I have for L square eigenvalue is L plus 1, for LZ square it is M square, and for LZ it's M, and this H bar square is common, LM, LM. So since this is 1, and I can take M common from here, we get L into L plus 1 minus M into M minus 1 square root, and there's an H bar here. So this is the magnitude of C minus, which means that this operation can be written as that L M minus first state is equal to L minus Lm divided by H bar L plus 1 M minus 1 square root. Because I can take this C minus under this, so using now this relation I can find the L minus 1, L minus 2 and so on spherical harmonics. So let's do one quickly. Okay, so I have YLL and YL L minus 1 can be written as L minus applied on YLL divided by, from here, H bar L into L plus 1 minus, and my value of M here is also L, so this is L minus 1 square root, so this gives us YL L minus 1. So I can substitute value of YLL from here, and this constant comes out of this operator. We have minus 1 power L over 2 power L, L factorial, 2L plus 1 factorial, 4 pi. Now, if we look here in this term, so I can take L common, this becomes L into L plus 1 minus L plus 1, so this is L into 2, so it's 2L. So since it's in the square root, I can put it inside this square root. And for L minus, we have, let me write it here, L minus is H bar, exponential iota phi, partial by partial theta plus iota cot theta partial by partial phi, and YLL, this part has already gone out of the operator and this is still there, so exponential iota L phi sine power L theta. Let me see the operator is written correctly or not. Sorry, there's an error, there's a negative sign with this derivative. Okay, so now I can simplify it a little bit and see that YL L minus 1 is equal to minus 1 power L over 2L L factorial 2L plus 1. You see, if I open this factorial, it is 2L plus 1 into 2L into 2L minus 1 and so on. And that 2L can be cancelled with this. So it's essentially 2L minus 1 factorial 4 pi like this. And now let's apply this operator and this, and we can see that minus, so its derivative is L sine L minus 1, derivative of sine theta is cos theta, and when this is applied to this exponential iota L phi, iota L comes out, so iota square minus L, and exponential cot theta, exponential iota L phi, sine L theta. The sine L theta remains here. So similarly with this term, there is an exponential iota L phi. So this is what we get from here, and more simplification, I can write it like this. Exponential this 2L factorial 2L plus 1 2L minus 1 factorial 4 pi, and the terms that were, there were two terms which were adding up, I can actually combine them in a single term like this. Sine 2L theta. If you open this up, and this derivative d by d cos theta, let me just say what it is. It's just a shorthand notation, because d by d cos theta is nothing but d cos theta by d theta, d by d theta, and this is proportional to sine theta, d by d theta. So this is just a shorthand notation of this derivative. Now this is our spherical harmonic for L minus 1, and similarly we can apply the lowering operator to this state. There is a constant here, and simplify it. If we do that, what we get is minus 1 of L exponential iota L minus 2 phi 2L L factorial 2L plus 1 2L minus 2 factorial 4 pi into 2 1 over sine L minus 2 theta d square d cos theta square sine d by theta. So I'm giving out the derivation, but it's pretty straightforward. Okay, so this is our spherical harmonic for the next lower value of m, and we can continue, and we can go to m is equal to 0. Same thing. And from this, I can write the general expression that for any value of m, this is minus 1 power L iota m phi. Here m was n minus 2, here m was n minus 1, so in general it's m to L factorial. Similarly, the term inside the square root generalizes to this is a little bit difficult to see without doing a couple more terms, but you can check, for example, when m is equal to L minus 2, this is just 2 factorial, and this is L minus 2, this is just 2L minus 2 over here. And those terms would be sine power m theta n minus m, because this is second derivative. When it was n minus 2, so in general it's l minus m b cos theta l minus m. This remains sine 12 theta because it was sine 12 theta here. So this is our expression of spherical harmonic of any order L and M. Okay, so let me just summarize that what we did was we wanted to find these eigenfunctions, which are simultaneous eigenfunctions of L square and LZ operator. But what we did, that we started by finding the eigenfunction for m is equal to L, which is the maximum value of m, because when we apply a raising operator to that, we get 0. So we started from that simple differential equation and we were able to find YLL, and then from YLL we applied the lowering operator, we found this, we applied lowering operator again, we found this, and here we have generalized it, just as we did when we were treating simple harmonic oscillator. But the method over there was the opposite of this. We started from the lowest state over there, and then once we had found lower state, we obtained the higher order, let's say nth state, by applying the raising operator n times. But the basic philosophy is the same. I would just like to point out, before I move on to discuss some examples of this function, that you can also obtain these functions using an alternative method, that we know that we have a form of this L square operator in spherical coordinate, so we can simply solve this differential equation, because this is a second order differential operator, and we will see that if we solve this differential equation, we come up with the same solution as we have listed here. However, this differential equation is a little bit difficult to solve. We need the series solution method that you probably haven't studied yet in your applied math course. But you can always do it in this way as well. Okay, so let me now take a couple of special examples of this function, which I can write here for easier comparison. Maybe let me go to the new board so that we can discuss them as well. So for L0 case, there is only one value of m, which is m0. So for L0, m0, if you put L0, m0 in that equation, we get 1 over 4 pi. Which means that the spherical probability distribution y00 mod square is 1 over 4 pi. Similarly, for L1, m could be 0, and if m is 0, then the function becomes 3 over 4 pi cos theta, and when m is 1 but m is either plus 1 or minus 1, it becomes plus minus iota phi sine theta. And the probability distribution corresponding to this is, of course, 3 over 4 pi cosine square theta, and probability distribution corresponding to this is 3 over 8 pi. And when we take mod square, this phi goes away, even though the wave function is phi dependent, but since phi is only giving us phase, it's not going to come in the probability distribution. So this is sine square theta. So how can we visualize these probability distributions? So let me begin with the simplest one, y0, 0. So if I have this coordinate system, and this is a spherical function, in general it's function of theta phi, but in the special one we either see none or we only see theta. However, for these functions, we can use what we call a polar plot. In polar plot, we draw a curve such that the distance of any point on the curve to the origin is proportional to the probability in that direction. For example, for this one, it's independent of theta and phi, so we have circle in any plane we choose. For example, if you choose YZ plane, it's still circle. If you choose ZX plane, it's still circle. If you choose YX plane, it's still circle. Which means that in 3D you can imagine its plot to be like a sphere, because each point on the sphere has the same distance from the origin. It means that the probability in this direction is the same as the probability in this direction, as the probability in this direction, and so on. You can actually see it in this way as well, that this line, which is the theta 0 line, its distance from origin, and this line, which is, let's say, at theta is equal to 45 degrees, this length and this length is the same, so probability of finding the particle in this direction or in this direction is the same. Remember, in these derivation we didn't consider r, so we are assuming that r is constant, that you can, for example, if you are talking about hydrogen atom, you can fix your distance from the nucleus at one point, and then these functions can tell us the probability of finding along different directions, keeping the distance from the origin the same. But that distance from the origin is something different than this. This is not that r. Okay. So in this method, this thing has a spherical plot. What is the plot of this function? So to plot it, we note that, let me use this red color for this, that at theta 0, this is 1, at theta 90, this is 0, at theta 180, this is 1 again. So it means I will have what we call a figure 8 plot, because if you see this curve in YZ plane, it means that theta 0 line, this is longer than, let's say, this theta 60 degree line. So 60 degree line has only this length. So from here to here, it means the probability at theta is equal to 60 degrees is smaller than probability of finding the particle along z-axis. So similarly, if we want to find the probability along this direction, we see that the distance to the curve from origin along this direction is 0, so you can find particle in the xy plane, because in xy plane the this function is 0, theta is 90. Another thing to note is this, that this is phi independent, which means that the 3D plot of this 3D polar plot of this function is just a figure of revolution if you revolve this 8 figure around z-axis. So you can imagine a balloon which has been stretched along this one, this z-axis, and in the center it's pinched that it's touching itself. So this sort of balloon type, elongated balloon, is the 3D probability polar plot of this y10 function. Since this is like a distribution along z-axis, this is also sometimes called PZ orbital, and this spherically symmetric orbital probability of finding particle in any direction with equal probability. This is the S orbital. And let's now see this one. This function is sine square theta. It means that this has a behavior different than this, that at theta is equal to 0, this is 0. At theta 180, it's 0, but at theta 90, it's 1. It means that If I make its plot in YZ plane, it would be like this. And that along theta is equal to 90 degree, the distance of the point on curve is maximum from the origin, so maximum probability, smaller probability in this direction, zero probability in this direction, and so on. But since this is also phi independent, the 3D plot of 3D polar plot of this probability distribution can be generated by revolving this yellow curve around z-axis because it's phi independent. And that becomes like the surface of a donut with a very small, infinitesimally small hole at the center, and the thickness of the donut surface increasing as we are moving away. Okay, but this is not a realistic orbital for an electron in a hydrogen atom. We can construct the orbital corresponding to this function. If let's say I make a superposition like this, if I take y minus 1 and subtract y11 and divide by under root 2 to keep it normalized, I get three over 2 pi sine theta cos phi. This, by the way, can also be written as 3 over 2 pi x over r. Because if I write r here and divide by r, this r sine theta cos phi is nothing but x. Similarly, I could have written this y10 as like this, that this number could be replaced by z over r. And if we add these and multiply by iota, we get 3 over 4 pi sine theta sine phi, which can also be written as 3 over 4 pi y over r, because r sine theta sine phi is y. Now, the plot of this function, which is actually it's square, so if I plot the sine square theta cos square phi, it is something like this. In the along x-axis, it has this elongated balloon shape. So we can actually imagine its 3D shape as a balloon as we had along z-axis, but it's now along x-axis, and it can be generated by revolving this figure 8 around x-axis. So it has the same probability distribution as this red color curve, but this is around x-axis. Similarly, if we plot the square of this function, we get, let me use this one, we get a balloon type figure along y-axis, but this one is different than the earlier yellow that I have put here, which was for this y1 plus minus 1, because that yellow, when it was rotated around around the z-axis, was a donut. But this function has a plot which is obtained by rotating this figure 8 around y-axis. So it's an elongated balloon type shape along y-axis. So that's why this is called py orbital, and this is the Ex orbital. We already have Pz orbital from here. So using the spherical wave function, we can construct the probability densities of finding electrons in a hydrogen atom, in a single electron atom. These description of orbitals are very important, and their functions, because, for example, you want to study dynamics of a particle, let's say in px orbital, that you are given that we have an electron in px orbital, Maybe the electron is part of a molecule, and that px is a bonding orbital between two atoms, or maybe it's just an orbital which is part of a single atom. Doesn't matter. But if it is the electron is, let's say, in px orbital, it means that at some time it is in one orbital in one state. Using the time evolution operator, we can work out its dynamics as time passes. For example, usually in the presence of magnetic field, these orbitals process around the axis of the magnetic field, that we can work out using the eigenfunction description of orbitals that we have developed here. Okay, so that's all that we have to say about spherically about the orbital angular momentum eigenfunctions for a spherically symmetric potential profile or central potential profile. Thank you.